So this is what they mean. The first one says that the divergence of, well, D is a displacement vector. How far are we going? The electric flux through a closed surface is the charge inside. So all I have to know is how much charge is inside this surface. I know how much electricity is going in and out of it. In a magnet doesn't create magnetic flux across a surface. It can induce other things, but there's no magnetic directly out of the surface because electric fields and magnetic fields are mutually perpendicular. The curl of the electric field is the opposite of the directional change of the magnetic field. Wait a minute. Electricity is going through the wire, then the curl, that's the magnetic field created. That's how we get electromagnets. It's also the other way around. If you have a moving magnet, you get an electric behavior. That's the way a generator works. And Ampere's law says that the change in magnetic intensity is displacement current and the displacement modification. So that's how current is moving. So yeah, all of this stuff that we're doing is the rules behind electricity and magnetism. Hello. And for the record, I apologize. Yes, it was light damage, but it's old. Copyright 19. Anyhow, chapters 16, sections 7, 8, 9. What questions do you have?
I'll figure out the integral for 16,728.
16,728. S is the surface. D equals X sine Y. Zero less than X less than 2. And Y from 0 to pi. Oriented up. Okay. It says evaluate the surface integral f dot ds, which is the same as the surface f dot n ds. And the vector field f in this problem is yz, zx, xy. Right? So talk me through this.
So I did the dot product. Oh wait, I did and yeah, and dot ds.
So what's n?
N is the negative gx I minus gyj plus 1k. And then it would be divided by the square root of the negative.
And ds is going to be the square root of gx squared plus gy squared plus 1 dA, right? So those pieces are going to cancel. So really all I need is this. So minus gx. There's g right there. And I get partial g with respect to x.
Negative sine x, negative x cosine of y and 1.
Okay, so you did the whole thing. Okay, no, I was confused, but now I get it. Gy is derivative sine is cosine. Okay, so I get minus sine y, x cosine y, 1. And that gets dotted with yz, zx, xy, right? But I can't use z. What do I use in place of z?
Is the second term negative or no?
Yes.
Say
But-
that again, the question.
So I can't use z here. What do I use instead of z?
The sine x sine y.
Right. So this is going to be the actual integral of f dot n ds is going to be the integral of y times x sine y, comma. Well, now it's that same thing times another x, so I'll get x squared sine y, and then xy dot that, right?
Yes.
Minus sine y minus x cosine y 1 dA over whatever the domain is. Okay. The following is now going to just be sucky algebra. I'm going to do the dot product. So I'm going to get x, y, sine squared y with a minus sign. Then I'm going to get plus, well, there's going to be a minus sign there, so that'll be minus x cubed sine y cosine y, and then plus xy dA. What's the domain D?
0 to 2 and 0 to 5.
So now I have to decide, am I better off trying to do this integral dx dy or dy dx?
Yes.
Okay. So if I'm going to do it dx dy, then I'm going to go 0 to pi, 0 to 2, all of the same stuff, dx dy. So tell me where you're having problems.
Mine is when I do that and I get to the y.
Okay, so let's do the x part. I'm going to get 1/2 x squared from 0 to 2, y sine squared y, 1/4 x to the 4th, 0 to 2, sine y cosine y, plus 1/2 x squared, 0 to 2 times y. X squared, 2 squared is 4, so I get a minus 2 there. 2 to the 4th is 16, divide, I get a 4. 1/2 x squared, that's a 2. Right? And now I'm integrating that 0 to pi dy. Okay. This is the one that's going to piss me off. That stupid sine squared there is going to bug me. This one's okay because that's a u substitution. This one's okay, it's a polynomial. This is the one that's annoying. So let's do that one separately. First thing I need to remember is the sine squared formula. Cosine 2 theta is cosine squared theta minus sine squared theta. So sine squared theta is 1 minus 2 cosine theta over cosine 2 theta over 2. Actually, I can never remember if it's plus or minus. I got to walk through it every time. So that 2 will cancel with this 2, right? The over 2 down here will cancel with the 2 up here. So minus 2y sine squared y becomes minus y times 1 minus cosine 2 theta, 2y. So integral from 0 to pi minus y plus integral 0 dy. Integral 0 to pi y cosine 2y. That's integration by parts. I still haven't done these two pieces. I'm only looking at this one. So now this is integration by parts here. LIPET, polynomial. I U is the V, is the Y. So dV is cosine 2y dy. What's V? And du is dy. So that becomes the integral, becomes uv, 1/2 sine 2y times y, 0 to pi, minus the integral from 0 to pi v du, 1/2 sine 2y dy. That's easy. That's also easy. Yay. Is it short? Hell no. When did we do integration by parts? September. When did we do trig integrals? That was chapter 3. So that's what? At the most recent, that was March a year ago. It might have been October a year ago. It might have been more than a year ago. Yeah, been a long time, man. We also still have to do those other two parts, this integral and this integral. So we'll have this number plus whatever the result is for doing those two as well. As an aside, Mia, you said that when you were doing this f dot n ds, you calculated n ds first. But remember, if I know that, and I know that s is a surface, then this integral becomes minus p gx minus q gy plus r dA. And that's what we got when we did our dot product right there. So that's a shortcut that I don't have to separately calculate g, x, gy, and the square roots and cancel it. I can remember it goes straight to that. I don't have to, but I can. I'm the same kind of person that you are. I would go through from scratch. It's F and N. I need N, I need F. Let's cancel whatever we can. But that's because I didn't ever remember this shortcut until I've used it for like 3 or 4 years. You gotta get it. You should be writing. Better? Wonderful. More questions. You made it.
Yeah, I've had really like weirdest morning. The weirdest chain of events happened before coming here.
I just want to know if you were able to check out properly this time.
No, this is not this time either. This time it was, they like held me back because I sent them my ransom, but they said they didn't have like one. So then but they didn't tell me which one. And I had to like look through because the person didn't know what it was called either, so I had to look through all of them and I had to find it and resend it, and it was like, that happened, and then I get into my car, it says that I have 0 gas. Like, that's not gonna go, so then I stop at a gas station.
And they have 0 gas.
Well, I go inside the gas station, like, well, not, I get out of my car to go pay. I forgot my wallet. So then I had to go inside, do the Apple Pay, but I didn't have my Apple Pay set up. So then I had to, like,
You're here.
yeah,
Okay.
it was like, dude, it's been a crazy.
Holy smoke. Jack, I don't think you should go back to this school.
Yeah, but then the crazy thing is, it turns out my gas gauge is broke, I had gas. So then I had to go back inside because I paid in there, and then I had to get a refund. Like, because, and it was, yeah.
I see a trip to the car shop.
Yeah.
Hi.
Yeah.
All right. Question.
From 69, number 4,
Talk to me.
it says verify.
Right, so I want you to do it both ways. Well, but think about this.
I
The
was
surface.
trying to set it up, but I just couldn't figure out how to set it up.
Okay, so the surface has 3 parts, right? So let's think about the surface integral. F equals x squared minus yz. S is y squared plus z squared less than or equal to 9. And 0 less than or equal to x less than or equal to 2. Hey, that's a cylinder, but it's laying on its side. It's pointed out at you. Okay. So if I want to do the double integral over the surface of f dot n ds, I say that's the triple integral of the divergence of f dv. But since this says verify, I need to do both parts. I need to do the triple integral, get an answer. I need to do the double integral and make sure I get the same answer. So I'm going to start with the setup for the double integral. Because the double integral depends on my surface. It's a cylinder, right? And it's going in the x direction. And the circle is y squared plus z squared less than or equal to 9. That's a circle of radius 3. So I've got the front disk, the back disk, and the side. Front disk, back disk, and the side. Right? Those are my 3 surfaces. Let's figure out for each of these, what's a normal vector? Let's think about the front disk. What's the normal vector? It's the one pointing right out at you. I. What about for the second disk, the one in the back? Because it's pointing the other way. What about the side? Which formula? Now I have to decide, how is this surface described? Is this surface the graph of a function? In this case, it would be x equals function of y and z. Can you describe that surface as a function of y and z? What's our equation for that side? The cylinder itself. What's the equation for the cylinder? And that means it's not going to be a function because it fails the vertical line. Right? So I can't do this as a function. I have to do it parametrically. Let's think about this parametrically. I'm going to do this as an R. So let's think about this side. If I wanted a point on the side of this cylinder, I need to know two things. I need to know where I am on the circle, and I need to know where I am along the x-axis. I have a parameter this way, I have a parameter this way. The parameter this way is just x. How do I determine where I am on the circle? Using theta. What's the radius? R of x theta equals. Now you know how to get the normal vector, right? I take Rx cross R theta and divide by the length. But I'm going to really, really, really be happy about that because Rx is and R theta is but easy stuff, right? And when I do the cross product, a lot of that is going to go with a negative sign. Yes, good catch. Where a sine is cosine, is cosine. When I do the cross product, a lot of that stuff is going to end up being zero. Not all of it, unfortunately. Would be nice. Would be so nice. But no, because I'm doing the cross product, Rx cross R theta ijk 1 0 0 0 minus 3 sine theta 3 cosine theta. That part is zero. But that part's not. And that part's not. So that there are some of these that are going to be zero, and some of these are going to be easier. And then when I do the length, it'll be a bunch of trig, and it'll be sine squared and cosine squared, and that's going to make my life really happy. So it turns out that the normal vector is not as psychotic as we think it is. The difficult part of this is setting up R.
So when you do that,
Yes.
it's an integral.
So I'm going to end up with 3 integrals.
So would you have to, when you do F dot,
F dot NDS.
do you have to plug in the parametric equations for F?
But remember, what's our F? So it'll be X X is just X, isn't it?
Yes.
Y was
30%.
minus 3 cosine theta. And Z was, hey, wait a minute, you know what we forgot to write down? We forgot to write down what the boundaries were for X and theta. What is X between? What is theta between?
0 and 2, no, 0 and, yeah, 0 and 2 and 0 and 2 5.
Because I'm going all the way around a circle. And then I'm going to take this and the cross product, right? And dot those together. I'll divide by the length, but then I'll multiply by the length because of the ds. See what happens to my lengths?
Yeah.
They cancel. All I need to do is this dot product.
So what would BS be for the other, for the caps?
Okay, so that's where we have to go back and look at the cap, right? So do you want to do the front disc or the back disc? So if we're looking at the front disc, DF, I'm thinking of the circle, right? And that circle is y squared plus z squared less than or equal to 9, right? What is the x value there?
2.
What about the back disc? But everything else is the same. What's the easiest way to do this integral? You're integrating on a circle. R goes from 0 to 3, and theta goes from 0 to 2 pi.
Is there, but how do you get like the DS?
Oh, so here I'm thinking of my graph as a surface, right? It's a disk. Well, that's x equals, isn't it?
Yeah.
So what's the derivative with respect to x? Sorry, the derivative with respect to y. We're thinking of this as a function of x equals g of yz. Instead of g of x, gy, right? We're thinking, instead of doing it this way, we're doing it this way. Instead of doing it up and down, where z is a function of x and y, we're doing it in front, where x is a function of y and z. What's the derivative of x with respect to y? What's the derivative of x with respect to z? So what the square root of 0 plus 0 plus 1 is?
Oh, so that's, so that's the kind of.
It's a much nicer integral this time because that's a flat disk.
The first equation, y squared and z squared equal to x, and that is.
But yeah, okay, because that if x is not y squared plus z squared, that would describe a paraboloid, right? Not a flat disk. X is a constant. Yeah, this is the part where it's like, well, what does this piece look like? It looks like this. So how is it changing? It's not. Yay! Which means that ds part is 1 dA. Then when I switch to polar, I'll get RDR data, and I know how to do that. Okay, okay, let me phrase it this way. This might help, it might not, I don't know. Remember that the weird part about a surface integral is to adapt the fact that the surface is bent. This cap is flat. That's why ds is 1, because it's flat. The Jacobian of the transformation from the disk to the disk is an identity. Its change of area is 1.
Fourteen times 675.
15, 8, number 10. Okay. Okay, so let's start at the beginning. It says, I want to evaluate the work done by F going around the path, where C is the curve of intersection of the plane, Z equals Y plus 2, and the cylinder X squared plus Y squared equals 1, and F is 2Y I plus X is EJ plus X plus Y K. Yes? Okay. Fabulous. I want to start with a crappy picture to help me understand what's going on here. So I'm going to think about this plane. Right? The plane Z equals Y plus 2 would have a slope of 1 and an intercept of 2. That is a tilted plane. Yes? And then I have a cylinder, X squared plus Y squared equals 1. Right? It's going to go up here and it's going to hit this surface and give me this ellipse stuck up in this plane, right? So this is my curve. And I oriented it positively so that as I walk around it, the inside is to my left. Why I do the orientation on it. But I can think of that as living above the circle, right? So the surface inside here lives above the disk there. The surface S is part of this plane, isn't it? It's the part of that plane that's inside the circle. What does Stokes' theorem tell me? Instead of doing the edge, I can do the double integral over the surface of curl of f dot n ds. But the surface is a function z. So I can get this n like that, where the function g is the surface itself. But I need the curl of the vector field, right? And the vector field is here, so I got to do the curl as well. I, j, k, dx, dy, dz, 2y, x, z, x plus 1. Me so far? I haven't done this yet, but when I do, I'm going to get some expression in x and y and z. I haven't done this yet. I'm going to get some expression. This is just in x and y. What do I do with the z here? I want stuff in just x and y. What do I do with the z in here? I don't need parametric because I have x and y. I'm not doing anything parametric up here. This whole thing is in x and y. I have z in x and y. Everywhere I see a z, I'll put this.
Yeah.
And then I'll end up with a double integral of a bunch of stuff, dx dy, or dy dx, I'm not sure which. And that'll be over the circle, x squared plus y squared less than or equal to 1. Because that's the base where my surface lives. And that function will be over a circle. What should I use on a circle? Once I have it all in x and y, do it in r and theta. That integral will be a lot easier in r and theta. Now, I got to figure out what this is. I got to figure out what this is. This part's going to go away because of the ds, right? ds is gx squared plus gy squared gesundheit plus 1 dA. So those pieces will cancel. And then I end up back at an integral that looks like this. I'm glad it didn't say verify, because if it said verify, I'd also have to do the integral on the curve, right? But given that this is a ellipse living above a circle, actually doing the line integral might not be that ugly. Might. Better?
Yeah.
More questions? Remember, 12, 13, 15. Well, I was just saying it's 10 pages. And most pages have 1, maybe 2 questions on it. So, yes. But you'll notice how much we're putting together, right? So I can't ask you to do like six or 7 of these. We'll be here for a week. You only have 2 hours.
2 minutes. I know.
Yeah, it's 8 to 10,
Okay.
but I'm soft on ending times. Ish. There might be another exam here at 10:30, I don't know. Exams are every 2 hours. I have 30-minute break in between. So 8 to 10, 10:30 to 12:30, 1 to 3, 3:30 to 5:30. Yeah. And then night class. Have fun. So, night class does a final. Sure. Final exams for night classes happen during the night class period, which means Monday night finals are Monday night. I will be emailing you all my office hours and stuff because after Monday, my schedule goes to hell and back. But I have office hours on Tuesday and Wednesday. So if you've got questions, come from me. That's for next week. I will answer any other questions you have about the final on Monday. When I remember to bring it with me. More questions. You get a new index card. You get to use all the previous index cards. That work? Yeah, make sure you got them. That's why I keep giving back to people. But leave that. In a sense, all of these theorems that we've done in chapter 16, they're all the same theorem. They're really all the fundamental theorem of calculus. Fundamental theorem of calculus says, hey, I want to add up all of the changes between here and here. I just need to look at this antiderivative on each end. For a line integral, instead of looking at f prime, we look at the gradient of f. But it's still the same thing. Look at the ends, subtract the two ends. So this is a flat line integral, this is a curvy line integral, but they're the same thing. Green's theorem says I want to look at the derivatives and add up all the changes. Well, let's look at the antiderivative bits along the ends. The edges of our region become the edge of our region. Stokes' theorem just takes Green's theorem and pushes it up in the air. So instead of our surface being flat in the xy plane, it now bulges and we have those du dv grids. And the divergence theorem says, oh, if I want to look at the derivatives on the inside, I can look at the outside's antiderivative on the edge. The edge is a set of surfaces. It's one theorem. Add up all the changes inside. Look at the edge. You just have to be able to find what's the right antiderivative part, which is really fundamentally what all of calculus is about. How do I undo this derivative process?
What page is that?
Page 1147. This technically is the next section in the textbook. It's one page. That's it. Really, this is what all of this chapter comes to say. It says the fundamental theorem of calculus works in any number of dimensions. This is the version that's one-dimensional. for straight lines. This is the version that's one-dimensional for non-straight things. This is the two-dimensional version, flat. This is the two-dimensional version for non-flat things. This is the three-dimensional version. I can go further. You can actually generalize this idea to any number of dimensions you want. You just then have to figure out what's it mean to be three-dimensional versus four-dimensional versus five-dimensional, and how do you find the edge? And there's this lovely discussion on something called manifolds. And my first graduate school calculus class, the book is this big, and it's called Calculus on Manifolds. And all it is are these theorems generalized. Like that entire scenario. But you do it in as many dimensions as you want. Why? Because all of these crazy physics people are working in 11-dimensional and 12-dimensional math. Yeah, because it works. Because of these three theorems. It's so cool. All right, Monday. These three sections are due. I will post the keys. I will post the review sheet key. I will answer whatever question. Have a wonderful weekend. Email me any questions you got. Know how it came back so I can actually answer you. I will see you all on Monday. Have a good one.
When do you come back?